Welcome everyone to this live stream. Guess we are live. I also wanted to continue here with the reverse engineering of this fine Matrox card here, also this time with more daylight. The last time playing Quake 3 on this, little bit darkish, and here's a precious, although not really Parhelia, but the die shrinked version p690, which at least is more energy efficient and stuff. Here of this fine, anyway, in case you are into hardware there, one of the first dual core CPUs, AMD Athlon 64. So when we write low level drivers, you have seen this in the previous videos. Normally it is of course the most efficient with some proper documentation here. Let's, for example, take a look in the proprietary and confidential Matrox MGA G400 specification. And you have seen this in the previous videos, Verge Voodoo, Matrox number 9, and many more here, and Silicon Motion Link 3D. And you would normally study this and architect your driver and then write the source how you best think this fits to the rendering pipeline and make use of all these hardware features. Unfortunately, in this case of, for example, this, but also NVIDIA, so if you have some hardware you want to write some driver for, whether it's an SGA Octane, Sun, Spark, NVIDIA certainly some candidate, or ATI and others, and you have nothing, then unfortunately we must, or are forced to resort to reverse engineering. And what this means is analyzing like a detective here all the bits and pieces and trying to make the most information out of this. So with that I have here two secure shell connections. So one thing, of course, you could always disassemble this stuff, which I'm not necessarily always the biggest fan of. This it's often also very time consuming, and maybe we do this another day, but just to give you an idea, the easiest is of course just dumping this with, I also hope I have it here actually, dumping this with object dump, or of course Idea Pro or Ghidra. And maybe we do this another day, but not today, but probably can already share, like, and subscribe for that. This is the X driver, thankfully user space binary 740, and so the easiest thing, you could object dump D for disassembly, demangle for C++ symbols, and then we have the text section here, somewhere of that sort. The rest is not directly code, and then you could either manually or with other tools like Idea Pro, the NSA's Ghidra and other tools like that, more professional, like more readable disassembly, and visually make use of this. Also, this Idea Pro and Ghidra have more automations to already pretty prints here to more readable C code and analyze the stuff of stack layout and use of variables and stuff. Also, I'm not really sure. I have the feeling Matrox might intentionally also, yeah, it was, even this is so hilarious, right? I said this in the initial live stream. They could have made friends and made this here, just releasing the specification, and get like all the Linux fans from the previous G200, G400 use it, because certainly it was a relatively rare niche and not the most successful card. But I'm really surprised. It looks to me, reading this a little bit, it looks to me that they obfuscated this at least. So this looks to me that this functions names are MTX37. I have no idea if they used an automate. So this normally should be, for example, let's show you hardware cursor. Here's somewhere hardware cursor init, and this obviously similar to other Xorg drivers initializes the Xorg's X isolated architecture hardware cursor stuff. And you see here already that filling in some structure. They also have here some here like for 3E20 hex MTX. So this is MTX 63, 64, 65, 66, 67, and I'm pretty sure these are hardware cursor enable, disable, position and load. And normally they should not show here as MTX. So I'm not sure if just stripping this would lead to this, or if they really spent the time and effort for this niche card that is not NVIDIA or ATI and used either some low-tech stuff of how can you do this, like obfuscating this. Low-tech is just using a define like preprocessor and manually substituting there some function names, so like substituting like define MGA, Parhelia, or MTX cursor enable to MTX 63 and so on. You get the idea. In either case, so this I'm pretty sure this is, for example, not sure whatever that is. Probably one of those is cursor enable disable. But anyway, so you see, we also see here already some registers. So there is some, thankfully, some function to write to registers MTX out register 32, similar to my own previous videos where we have done this for Virtual and Voodoo. And what this does is, if you take a look at the specification, again, this is not the matching specification, right? This is for the earlier G400, and I read on some corners of the internet maybe the successor was G800 or something, which might have became the Parhelia. So this is, you have here some register like EC, and again, this is not the right documentation, right? Just as how this would normally add up. You have here some register names for all the hardware function stuff, and here, so for example, there would be, I think this is a little bit strange here, whatever they shift here together. In DX, I'm pretty sure this out register thing takes a register in EDX. Just we need here some, because they use here add. There was somewhere a more readable example. What was it even? This was register out register something. MTX out. Let's maybe just look for that. And so yeah, here EDX. So this would, I'm pretty sure on x86 with this function call layout for the specific MTX out register 32-bit thing, that I guess the register to be written is in the DX register, and this is 18cc hex. So this is why in the other cursor function there was a add. So they add there something together, whatever they do there. And maybe for this has like dual or triple head, maybe they have there some offset for the first, second and third CRT controller. Anyway, so this is, so you can disassemble this, but often it is also relatively convoluted, this example, because we have already Linux driver. It is a little bit easier maybe. If you have a Windows driver and it comes with some kernel driver and a bunch of DLLs, it might actually be extremely time consuming to disassemble all the DLLs and all the interaction and as a kernel driver and figuring out what exactly is passed there left and right. So what you normally, what potentially often is maybe easier and at least doesn't require you to disassemble this and understand all the disassembly, is to look like investigate and trace like kind of under the microscope, if you could like put a microscope just to visualize this. So how would you do this mechanically? If you have some mechanics, you take a microscope and look into there. Obviously we can't put an electron microscope on this, so we do this in software obviously, and the closest like investigating this in a microscope is like tracing the I/O, the input and output of this. And for this we already took a look the other day. I found already this memory mapped I/O trace that is in the Linux kernel for already 15 years or so. And what this does, this is a kernel driver that is in the Linux kernel since 2.6 whatever, and maybe it's even written there, but doesn't matter too much. And what this does is, this is intercepting I/O remaps in kernel drivers like the NVIDIA one, and then single stepping any access to this. So if the NVIDIA blob, the binary only object, is certainly requesting resources like PCI and memory mapped IO registers and the frame buffer, the VRAM, and writing in there like what you've seen on my previous videos, PS3 and such. And so we want to understand what's going on there. So this is one means, like doing this in the kernel. And that is also so you just need this enabled config MMIO trace. And actually there is no, maybe this. Where was this? Much to having the right side open. Come on, this is not exactly what I... So you basically just mount this debug FS from the kernel that is explained here. So if you want to use this, but we can't use this for this case, but for the NVIDIA driver or ATI and similar stuff, and you have Linux driver, and if you do this on Windows, then you would need to write something similar or use virtualization. So for this solution, you mount this debug FS, enable MMIO trace. And how this works is everything after you enable this, what is loaded is then traced. So you need to not have the NVIDIA driver or Matrox driver loaded, the thing under investigation. So do not have the driver loaded, enable this tracing, then prepare here this with catting this from kernel, this trace pipe to user space, and then load the driver and do your stuff. This will trace all the IO stuff happening in the kernel, which, for example, you can use for the NVIDIA stuff. The problem with that is that the Matrox driver is for the 2D stuff, which I want to trace first, not using this in the XORG server, and for simplicity, I even have not loaded the kernel driver right now. And so we need something else. And I also found here a really cool thing, a modified Valgrind, which probably you might have used already to debug memory problems in not memory type safe languages like C and C++ and stuff like that, or assembler. So the NVIDIA Novo developer have modified Valgrind with an MMT, memory map tracing tool. And you can check that out here from GitHub, NV Tools Valgrind. This comes with a new tool, MMT, and it is similar to the kernel side MMIO tracing, just that it's not doing that in the kernel, but in user space. So for the XORG, the old-fashioned XORG stuff that runs in user space, how it was for 20 years, we can run this here, and I've tried this already for the last days and nights a little bit. This is why this video is already a summary and not 4 hours trying and erroring around here. And so we run the XORG server with the Matrox driver in this Valgrind with this memory mapped tracing tool here, and specify it which file we want to trace. So it is intercepting all the file opens and memory mapped mmap memory mapped memory mappings, and then read and writes to those mappings. What took me a little bit while, I wasted a couple of minutes. Intuitively I had specified here /dev mem, because I naively and intuitively assumed, like back in the day, like decades ago, the XORG server would use the dev/mem, like whole physical memory device, to do the mapping, and I was wondering that I didn't get anything in the trace. And then I used strace to actually trace what's the XORG and Matrox MTX drivers actually opening, and it turns out this new stuff like libpci access and XORG driver is actually using this fine-grained on Linux anyway, this fine-grained sysfs stuff that you might never have seen before, so that it's only memory mapping here resource 2 and resource 0. These are the members here, memory add from the PCI device. So we have here PCI device 300 VGA compatible Matrox graphics Millennium p690, and these are the memory mapped IO. What was bar standing for? I just looked this up. Memory. Darn, I actually so much to PCI mem bar. What was it standing? This was somewhere like darn. was memory window. What was the memory regions? IRS, it was base address, membar, like memory base. I think it was like memory base address. That was it, what it was probably for. Let's fact check this. Memory address space stored in the base address of the regions is stored in the base address register. Yeah, bar base address register. There you have it. So you see already this card has 128 megabyte memory, not too shabby, right? So that is currently physically mapped on the PCI configuration side at F0000, usually very high in the address space, obviously. And the memory mapped I/O control registers, as seen on the Verge, Voodoo and stuff, similar stuff, 8K here, physically mapped at FEB, FE000. And those live here in, or are accessible in ZFS in modern systems, and that is what we are specifying here, Valgrind to trace, then writes this to log files and run the X server. I just like X, nothing too special, just without any windowing manager and any other fancy utilities. And just for simplicity also, -br is background, black background, and this was just for testing, no Silken mouse. It's a little bit more snappy mouse pointer handling stuff. I think this was just some testing around. Probably we don't even need this. So with this is secure shell, always good to run this stuff in secure shell. I also disabled the Matrox logo. Matrox Parhelia stuff was displaying there some fancy logo. I just disabled this because I didn't want too many register and frame buffer writes in there to minimize the data. These logs are already large enough. So you see we only have a mouse cursor. That is intended because we need some baseline. So how I worked on this is, because these logs are rather huge, after some trial and error I hoped I'd look at the log and recognize from all the previous years of experience, recognize some patterns, but that proved more difficult than I hoped. So this is why I captured here some baseline. So because this log is already 80 megabytes, so much to reverse engineering. It's not the most easiest thing to do, right? This is why we do this here live on this channel. The Novo people here have some tools here, NV tools, and they have some DMMT. So what this is doing is some small little program that is pretty printing and parsing this log. So I SCP'd this here from the 19268 Matrox Parhelia machine here. I could also network NFS mount or whatever if you're fancy. Here there's various logs, and as you see I have already a couple of those. First I was testing and trial and erroring around here, and then I decided, last but not least, because this became, I didn't recognize too many patterns on the first glance, and this is why I've done a reference run. So reference meaning just starting the XORG server and quitting it without doing much. So this is a reference. Then we parse this log file. So this means DMMT, for example, mode setting. This is what the log will look like. Here's some mmap trace here with these regions. You see here also like logs is open, so the XORG server and Matrox MTX driver are opening these resources here with flags and mode. This is a file descriptor returning 10 here, file descriptor 10. And then we get here the access. So this is specific to this tool. Of course, all the tools will print something different. You just need to read the freaking manual. So one is here the resource 2, the memory mapped I/O register for all the programming, and so the driver is starting to bit banging here all kinds of stuff, reading and writing whatever it's doing there, and yeah, that is rather long. It's 80 megabyte of fun stuff. And then also eventually, because we trace the memory mapped I/O region and the frame buffer, so this is the frame buffer, At least it should be, not really sure what is it doing here. So what it should do eventually though is, so basically this are all the register reads and writes, and of course right now this is only magic numbers and we need to decipher and find some pattern, like do some human pattern matching to understand what's going on there. Questions on what we're doing. We are reverse engineering Matrox Parhelia video graphic stuff just for the fun of it. So this 2 here should be the frame buffer, and also I'm not entirely sure why there are some, why maybe it loaded here. So apparently it did here something. So this is whatever it's writing there, maybe a cursor, maybe whatever. All right, actually it could be the cursor. Now that I think about this, because the issue is, let's also kill this away. We see in the, now that you see I stayed already some hours on this and figured some stuff out. Probably this is a cursor because for some reason I was actually wondering cursor, offset and aperture at 0, 0. So this is the log where it is saving the hardware cursor. So most likely it is writing there some cursor, although in my opinion doesn't make the most sense, but most likely that it's what it's doing there, because normally the frame buffer, often the frame buffer, like the visual representation of your pixels, starts usually at 0, but of course you can change this depending on your memory layout. So most likely this is a cursor, I guess, now that I think about this, and most likely it is changing this after that. Yeah, so actually it is changing this here, and this is also what I found already. It's live on YouTube, finding some more details. So I figured already that this here is the cursor base address, because the Matrox MTX driver is nicely printing this. As I said, you've just seen this. So this is cursor, offset and aperture 0. However, later it changes this to that address. I have no idea why it starts with 0. Doesn't make the most sense. Whatever strange memory allocation stuff they're doing there. So most likely, also I should probably, as a fun fact, the more videos I make about in-depth bit and byte stuff, the more, if people at NVIDIA or Matrox see this, they could obfuscate the driver more. Of course, for us it is pretty helpful that the driver is printing this out. If the driver would not print this out here, it would be one more clue that is gone. But as the driver is printing this into the log, it's one clue. So you need, with reverse engineering, you need to be careful to pick up each breadcrumb you can find there somewhere on the way. And if you see something like this in the logs, then always like save this and match this to the bits and stuff. Because so with long trial and error, I could already tell you that, this here with long trial and error, I already determined that this here memory mapped IO register 34 is the location, the hardware register location for the hardware cursor surface. I have this already here. I started some file in Emacs, not making this stuff up. Here's already, this is right now small. Let's save this and does MTXCC, yes please. I should have made this larger before the live stream. Emacs init 20, comment this out, and where is now my 100 millions of terminals. Also, fun fact, probably sometime soon I will start setting proper titles for the terminals. So here it is now larger for you to read. And obviously I've not yet done much. I've just deciphered in a couple of hours some basic stuff like this cursor, this apertures. So this cursor apertures are multiple times. I guess this is for triple head because this Matrox Parhelia supports triple head surround gaming with 3 CRTCs, like cathode ray controllers, good old-fashioned terms. So most likely this is 3 times repeated. I guess, like right now, obviously I have no specification. This is also why specification is more amazing, because then we don't need to reverse engineer this. But from common sense, I would guess that this is 3 times repeated, because triple had 3 video outputs. Another near accident today here live in Berlin. And so this is the aperture location, and this is the surface location. The difference most likely is one, also here modern hardware complexity. One is the physical location in VRAM, where it's stored in the hardware, the GPU's memory, and the other is like virtually mapped, most likely virtually mapped, some virtual memory window where we access it from the host CPU. In this case is AMD Athlon, most likely. Why they necessarily need this for this complexity, not really sure for me usually, but yeah. For other stuff, of course, for textures, it might make more sense to have this kind of aperture system, so that you can virtually map textures. That might make more sense than for cursors. How did I determine this? Of course, now that we look on this log, that it is first 0, it is first written there's something, and later changed. It might look for you like magic. I determined this by having here multiple log files. This first stuff I can probably delete, but as I said, I made some starting some reference log, starting and quitting Xorg, because this log, as you see, just running Xorg already 100 megabyte log, and that is certainly not the most fun to go through. And then I diffed this, right? So you have here already mouse and MTX and mouse. So this is like diffing, unified diff mouse, actually ref versus mouse here. And yeah, even this runs, this is 100 megabyte diffing this on a 4 gigahertz AMD EPIC Threadripping Ryzen 1350X. Even this diffs this 100 megabyte diff quite a while. So you see some, each time you run this, of course, some random different register reads here of whatever these counters are or whatever is programmed there. And then I basically also moved the mouse around a lot. So for example, here at the end of the log, so what I did is I started the Xorg server and moved the mouse around a lot, and also loaded a 32-bit RGBA mouse cursor with this Xorg cursor themes and moved it around over an Xterm, so that the cursor kept constantly changing. Actually, theoretically, I could show you that. This is also how we, on the P3, on NVIDIA, ATI, Matrox, whatever the case might be, you would do this, getting one little test case at a time. If a solid filled rectangle, solid filled triangle, a textured triangle and stuff, and then one after another decoding, tracing here these registers and determining which of those changes when you have your test case of one single derived test case and what changes. So for that, again, we can run Xorg. So running Xorg, I have this here. Usually I don't even look at this much. It's slightly slower because obviously it runs in Valgrind for memory mapped IO tracing. Now we have our cursor there, and then for this minimal test cases, I have here a second secure shell. Obviously, can never have enough of those. Then display 0. Also, this is mode setting. So we need one Xterm. So that would be Xterm here, and then wait a second. How was it? Also, we need to read this XRDB X resources for the cursor seam, and then X term. There was some certain order where there's only like one order. Yeah, this right, this somehow didn't work. There was something strange that with some X term also, yeah, fun strange X stuff. I found earlier already today that somehow this X resource DB stuff somehow does not necessarily work with just one X term. Anyway, I think this combination should work. One X term, and yeah, so here's our X cursor theme. What this means is instead of this X core protocol, 1 bit black and white or foreground and background color cursor, we now have a fancy RGB cursor. And again, the problem is if you move the mouse out of this window, this TVM draws here quite some window decoration. So you already want, pro tip, you already want to avoid this, because all this redrawing already causes quite some random stuff in your log, and you don't want this. So what you want to do is move, for example, just here on the window title, so that only the cursor changes and not any other redrawing happens, because all this stuff will result in memory mapped IO traces, so plenty of register. This might be solid fill, so this might be lines in this old-fashioned XORG stuff. So if you move out of here, I've not yet decoded this, but this might be solid lines, or for fancy like GTK plus stuff, this might even be certainly not fancy lines, but fancy blending of textures, of textured and even like mono, like text color expansion of drawing anti-aliased text stuff. So yeah, you want to avoid this, otherwise you have, say, already 10 megabyte of extra, hundreds if not thousands of register writes of blending their stuff. So just doing this here carefully on some corner, and you have already all the register writes, or you should have, if you don't have, so if you do this, and you should have hundreds if not thousands of writes in your log. If you don't, then you're tracing the wrong thing. Then you need to look carefully, need to look more closer, and analyze what other devices are opened, like in my case dev mem versus this device PCI and so on resources. So you're just looking in the wrong place, and you need to look more, and to look closer and in more detail. So now we have this trace. We secure copy. Either if you do this for days and weeks, you also want to network mount this, but for a start you can SCP this certainly, but after a while SCPing this over gets old. So this is exactly what we're looking on here, and we see most likely diffing this here, diffing the reference versus our mouse fiddling around thing, and so most likely this here are mouse changes, although the driver might not be totally, yeah. Fun fact, many proprietary drivers are not the most optimized, because it's rewriting here 1A74 with 0 and 3, so I've not yet an idea what that is, but obviously it's cursor related. Where is even my this here? So I so far determined, so this apertures are living here, memory mapped IO register in the beginning 10, 20, 30. Then this is a physical location, so the one is a virtual mapping or so. This here is a physical location, like this register 00, 10, 20, 30, 34. Again, most likely triple head, 3 CRTCs. Then this here is the cursor base, so let's take a look here. Does it make sense what I determined earlier? Certainly moving this around changes mostly the X and Y positions. So let's see, what have I decoded. So this is my own structure here, enum MTX registers. The cursor base should be Z, whatever Z is. 1AC4, that would be this one here. 1AC4, not yet sure what this is. It's some kind of cursor control. We further need to decipher that another day, what exactly this is doing. You see it's writing here 3, for example. And I think most likely from what I also deciphered, because this proprietary driver is rewriting similar values twice, I think one is the first and one is the second head, because it's writing, for example, this here, this cursor base thing, it's writing 3F. So this is apparently what physical memory in the VRAM, the CRT-C, the CRT controller thing is outputting. So I guess 18cc is the cursor base, the first head video output, and 1ACC is the second, because the driver sometimes is also writing this there in startup, and it's also writing this 3 or other values in 18C4 and 1AC4, and similar to cursor whatever a 1AD and 18 and 1A. My tongue's already twisting from all the hex values. I think the position is most likely, what did I have here? So 1AC8 is most likely the position, so that would be this one. So most likely, like, not yet sure, I would hope that this is X and Y. 18CA and 18CA, you see it is somewhat similar values, so most likely this is X and Y, I would hope. Anyway, you see, reverse engineering is often best guessing and fiddling around and staring at numbers and guru meditating for a long time. We can, so this should also update the cursor address, so this should be 1ACC. We should have multiple, so as I said, it is, so this is a diff, so it's writing here some physical location, and this time in this trace it's not writing another one. So what we would need to do next, what I've not yet done, we would need to write some example program and writing to this registers as well, either here on Linux like memory mapping, either this PCI, can we control C here? Yes, we can. So either memory mapping this this bus PCI resource 0 or resource to ourselves, or def mem, like I've done for the Lynx 3D, where I've written a full 3D engine control stuff. And so writing this couple of handful registers and double checking that this stuff that we have deciphered here, that it works like we thought it would. And then I've already done a couple of more things. So diff u, we have here also mode setting, and I've iterated here xrender mode setting, a couple of modes. And did I already, I hope this bloody loud car music there doesn't copyright match here. When YouTube can't make this stuff up. So mode setting is most likely all of those registers here, and we would need to do quite some trial and error to decipher what all of this, so what all of this registers, memory map register read and writes are. All those previous FPGA videos in the DOS examples, I usually have not done mode setting. Mode setting meaning controlling the video mode on the CRT control registers for, in this example, 3 video outputs. In the previous examples, I've usually done, except the Voodoo, I've done the mode setting with BIOS calls, because I was not the most interested in doing the mode setting. I was more interested in the video acceleration and 3D stuff. In some cases where no open source was ever done before, like the Imagine 128 or the Lynx 3D. And only the Voodoo 3DFX Voodoo we've done the mode setting, and for that you can watch the 3DFX Voodoo video. So we would need to program all the PLL, the phase locked loop, all the video mode parameters like front and back port, and all the timing parameters. And yeah, this is unfortunately the time-consuming stuff of reverse engineering, making sense of these numbers. And this would be, let's see, what are we diffing here? Even mouse versus, actually not mouse, we should diff ref versus mode setting, I think anyway. And yes, you see even AMD 1350X diffs here the stuff for 10 seconds or whatever, so the logs are that large. And as you see often, it's not always as clear as you would hope. Why is this log so small? Or do I have two mode settings? As so often, it's not trivial to map this. Often there are plenty of writes, and you need to make sense of this and do lots of traces and compare these numbers. The NVIDIA people and the Novo people have lots of tools, of course, tailored to their NVIDIA cards. I thought I had here some clearer pictures already. Do I have here something in my text file already? Cursors, mode setting, did I not paste mode setting into the... oh, darn. So, there should actually be plenty of more writes, so... we could redo the mode setting though, because some of the mode setting trace is right now not the most conclusive. But basically the mode setting stuff lives mostly in the beginning of this memory mapped I/O space. This would be plus write something. Yeah. Plus write whatever. Yeah. Anyway, so this would be yeah, will be quite painful to trace this. We can actually, you know what, repeats this. So to show you this in real life, so let's redo this mode setting. I found that so this is running here with just the Xorg cursor, not touching that though, because we want the mode setting. And I found that just doing the mode setting will somehow strangely restart this if there's not a client running. I'm also not sure where that is coming from. So we better start an Xterm. Unfortunately, this will add some memory mapped I/O stuff for filling this Xterm. I also can show you this. So this will obviously result in quite some solid fill and splitting there some text stuff. But this is just from experience that if we just do the Xrender, it will strangely restart the Xorg server, which I do not want, because then it's remapping these resources. I've done this already earlier. Then we can do the mode setting like 640 by 480. And this, of course, will do the mode setting here, as you can see, obviously, right? But we do not touch this here at all, because we don't want random stuff in the trace. 10, what is it, 10, what other, 1024 by 768 or whatever that mode was. It's just iterating here some modes, 10280 by 1024. Last but not least, 1600 by, what was it, 1200, right? And then 1920 by 6, what is it, 1280 or something. Also 200, maybe it's also 200. That it is. Anyway, so we're back. Of course, we are not even interested in this visual picture there, just to show you that this has some effect there. We are only interested, in the trace. Let's SCP it again. And yeah, 107 megabyte. Then empty something mode set of mtx mode set txt, and then let's rediff it and hope that this time the log is a little bit better, because last time I might have messed that up. reference to mode set. Let's see what we're getting, and yeah, diffing 107 megabyte. Maxing out on 3950X Ryzen. I'm surprised we have there so little, although maybe why is this log so similar at the end? Strange stuff. Maybe, by the way, how did we kill it away? Do we have out of range? So because killing it kills the Xorg server so much that we don't have valid video mode. Yeah, as I said, unfortunately, not the most easy thing to parse, and you are usually best off writing there some additional tools, and it's getting easier as soon as you have a handful of registers. It's getting easier as soon as you understand what this stuff is actually doing there. We're mostly interested in writes. You can even grab, so what you usually do is grabbing SEDing and AWKing. This is, however, filling this with black. I'm slightly surprised that we don't have more mode setting. A little bit, nah. This is also why I already prepared quite some stuff, because doing this for 5 hours certainly is not the most entertaining. But basically, when we take a look here, let's see, this is reading, whatever this reading is doing. I was not yet sure yet. This is reading here. Let's go back to the file descriptor 2 is the frame buffer. So maybe not the... You always need to, what would be cool is some, if we would have some ways to mark here this log to manually annotate it, but I didn't yet find there something. So this is basically where 2 is a file descriptor for the frame buffer. So this was filling it black for the startup there, and here's now starting Xorg server, whatever. So here's, it's reading something. So this is, I have the feeling this, we can also already document this. As you see it, the driver is doing nothing but reading this. So this might be some vertical retrace counter guessing from experience. Did I 1924 hex? Nope. So 19, so it's also reading here something. So it also read previously 900 times this one. But yeah, we need to further investigate this. This might be some, because I'm not really sure why the proprietary driver is reading this so often. Also, wait a second, did this just wrap there off? Yeah, it just wrapped here from 4D0, so whatever that is. So, and then 29. It's something, whatever it is. It's some sort of CRTC, most likely either vertical, horizontal retrace, whatever. This also means that maybe it makes sense when I said filtering this out, because this is totally uninteresting for us. So reverse grab that. So that would be something of that, and then we already get a much cleaner log. And this is how step by step you would remove the stuff that you're not interested in, filtering out stuff you know, you don't know. Here it's reading something, something like that might be, it's always reading F, so this might be some FIFO fill, like first in, first out, command FIFO stuff. We can also document this, and then it's always step by step documenting a 1 bit at a time, and FIFO fill question mark retrace, and this is how you 450, 800, whatever, and then you would need to map this here. So for example 1924, this matches here somewhere in the CRT1 region maybe. And from previous stuff, so we have here, not really sure, this is also a little bit strange, why does it, yeah, so this 1FC9 is most likely also some CRTC stuff, because this is at the end of our, I hope we are on the mode setting stuff, so this 1F something stuff here, this is most likely mode setting. It's also writing here several values multiple times into that, so this might be some indexed register of stuff we need to decipher more and maybe match to. Often you can match this if you're lucky to what they have done in previous generations, so some of the bits and registers might still apply, but maybe not so. The CRT stuff looks on the first glance pretty different from the G400. But yeah, that's how you're doing it, one step at a time. So 8F, I think we just commented this, right? 8F4, whatever that is. You see reading this also plenty of times. So we probably also want to filter this out, grab V1. This, that we have even less in this log to worry about. And then for the more interesting parts, we would need to, this is, by the way, 2 is a frame buffer, so it's writing here some real bit pattern into the frame buffer, maybe our X term. So this is how for days, weekends, nights, months and years, you would decipher this. If you tested and copy and pasted these values here for the cursor, first I would know how I would proceed is first make sure these cursor bits are correct and they do what they look like they do. Most likely, as we are Linux running, mapping here this PCI resources, maybe even try if we can map this while the Xorg server is running, and try to move the cursor around, so to fully validate that these are really the cursor position registers and this is the cursor base. Depending on what you need, if you're writing a new operating system like Redux OS or a Haiku or whatever the case might be, or an Xorg driver in Linux and BSD, you could continue with mode setting depending on what your priorities is. If you say, okay, mode setting is not so interesting, you just, for your hobby stuff, you just mode set with a VESA BIOS extension to your full HD mode, 1920 by 1200 or something, and just call it a day. And you're more, I personally don't find mode settings that interesting. This is of course whether if you write a real world operating system, certainly everything needs to work, and maybe the mode setting might be more important. But for me as a hobby, most likely some solid fills, lines, and later then 3D triangles, similar to our PS3 and Octane and other work here live on this channel. So this priorities depends. Is it like mission critical at work and maybe mode setting? Is it more fun stuff than, yeah, YOLO, whatever? Give me the bit BLT and texture filling. So yeah, this is how you would be doing it. I think it shouldn't be the most complicated, depending on, yeah, although this is DirectX 8 or something generation, so it has already vertex and fragment shaders, so this programming, it could also be even the G200 and 400 had already microcode, so they had here already some warp stuff, warp instruction stuff. And so even on those open source drivers, you have a binary only blob for Matrox G200, G400, whatever it's doing. Probably, I guess it's the setup engine, so the bytecode that is loaded there in the Xorg driver is most likely doing the floating point multiplication in this warp engine as far as I've ever seen in the last decades. So probably on the triangle setup, as in you pass in those values, they most likely, I guess, if you know more, leave them in the comments below. They most likely run through this microcode for the triangle setup. So we could be so unlucky, although right now I didn't really necessarily see, I think it didn't load microcode here, so it's doing here some stuff that most likely is not microcode. Whatever status or mode setting that is, read write, whatever it's checking there for not busy, or maybe it's waiting for CRTC not busy or something. It could also be generic stuff of the Xorg server before it's going into the Matrox MTX code. But you see pretty repetitive stuff. 3 or 4 read write, I have no idea why. Whatever, maybe. Often, anyway, in my experience, oftentimes proprietary drivers often do extremely inefficient stuff with whatever C++ Windows driver-based class hierarchies they have created there. But so yeah, this looks totally bogus, inefficient nonsense to me, so no idea why they are doing it. You're scrolling already a while. Whatever, maybe someday. So write, read, I've actually, this could actually be display data channel. So the display data channel is connecting some EEPROM in your display in all the modern displays of the last decades. So this could actually be bit banging some I2C DDC display data channel for reading the monitor information actually. So much to repetitive stuff. Calling it nonsensical, and it's your monitor I2C edit data. So yeah, in case you were wondering what takes so long on you, yeah, bit banging there 1 bit at a time. Maybe not, whatever. Let's maybe fast forward to some frame buffer write, which is this, and let's scroll back a little bit. What was before 1C4? What is this doing here? Yeah, some of this stuff should be mode settings. So somewhere after DDC probing, reading over an I2C bus display data channel, and your displays EEPROM or flash, whatever ROM stuff, serial flash, eventually mode settings. So some of this stuff again, so this is cursor, right? A40, what did I had here already decoded? 18cc something 18. So yeah, this is in my opinion most likely, so this is writing, this is most likely CCC4 40. So this is most likely phase locked loop, frequency programming stuff, and mode setting. Again, 1800 hex and 1A hex are the CRTs, in my opinion, from what I've seen so far. To be 1C is 1A, 1, yeah, whatever. Again, all this fine mode setting bits to be decoded another day. So this is cursor. I said this before already. It's setting here in cursor. We said this already in the beginning. So so this is most likely a fancy cursor. The cursor base address was 1ACC, so this most likely 1ACC there somewhere. Anyway, most likely cursor, and then so because this is stupid, again, inefficient stuff, right? I said this in the beginning. If you're tuning in, or as a reminder, no, in my opinion, but maybe this might not be the wholly inefficient. My driver would never do that, allocating a cursor at 0 just to later change it again. Although it might be an Xorg limitation, maybe it's getting this through whatever Xorg infrastructure, although probably it shouldn't, but yeah, your mileage may vary. Because then it's resetting this, as I said already before, and this is a frame buffer write of filling this with black. As you see, this is second file descriptor for the VRAM, all black, and so this should be the whatever, yeah, so this 3 whatever, so this is here the cursor aperture as we determined already, and this is some control bits, maybe like format, like bit depths or whatever that belong to that, I guess. And again, this is a physically, as a virtually mapped thing for the cursor. All right, anyway, no, I pressed the wrong key. We can scroll it. So anyway, let's see. So this is how you're doing it, one piece at a time. And I hope you enjoyed this and learned something here on our in-depth low-level educational stuff. Questions as of the usual surprising stuff you do here, this in-depth stuff. Let's enjoy some lemonade, because freaking hot. You do this in-depth stuff and people asked what VM is it? This is Blackbox, my 20-year trusty VM, and this, by the way, is our compiled from source Google Chromium here. Previous video, 2 hours the other night of finally compiling this from source, but also not for the faint-hearted, similar to this reverse engineering. But hey, it didn't crash, so my problem with the binary download from Google Chrome was that it crashed a couple of times on me. So far this built from source Chromium here with our fancy little built from source distribution, that is T2, is what I wanted to say. Yeah, it's not yet crashing. It's more stable so far. Who cares writes, are you affiliated with Xorg? No, not really. I just they're just nice people. At least some of them. I heard. Hopefully many, all or whatever. Just the social engineering and social media. There some people, and the Xorg Foundation people already, whoever it is, I have actually no idea. Some of them retweet this, also the previous Link 3D and other work. I sometimes edit them there on Twitter, and they were so nice to retweet this, which is certainly pretty cool. Thanks for the shout out. So who cares if you don't have the Matrox specification? Can you reverse it? Does this speak some non-protocol except, I guess so? This stuff doesn't speak a non-protocol, and I said this before. This is what this video was about. Also the comment was probably pretty old. This is exactly what we are doing it. So this is how you would, it's not some common protocol, unfortunately. The VGA stuff was all VGA compatible there in the 80s, and I said this before, I really wished the Sound Blaster cards were all cloned, and I really wished the cloning or those graphic vendors would have formed some committee or some working group, and they would have made some what Sound Blaster is to the Sound Blaster audio output cloning stuff there, some Sound Blaster or like SVGA compatible, because unfortunately all those graphic cards, all of them are incompatible, as seen in all the many of my previous videos. So we have done S3 Verge, we have done Cirrus Logic with a local bus, we have done ET4000, one of the first back in the day ISAR, and yeah, even ISAR card accelerators, so the very first 2D accelerators for Windows. And so we have done BitBLT and solid fills and similar stuff on an as old as T-Zeng Labs ET4000 there a year ago. And in the meantime, over S3 Verge and Voodoo and Link 3D, Silicon Motion Link 3D, and certainly not to forget our P3, but P3 NVIDIA RSX, but also number 9 Revolution 3D, Imagine 128, and similar. So and even this Matrox, I already wrote some bits for this Matrox. So my goal is here to write, and I said this before, write a collection of smallest possible usable hardware isolated code stuff for your playing along at home, writing DOS demos, homebrew operating systems, but certainly our microkernel, and showing you here how you do it. So we basically have zero knowledge, and this is with a couple of nights or afternoons, this is what you can derive. It's not yet much, and I still need to test this but I'm pretty sure this is how, with a couple of afternoons and nights, depending on your skills and tools, certainly next it probably would make sense to write some tools. And again, next you would need to have small derived samples of solid fills, lines, and then 3D triangles. But for the 3D stuff, we need to use the MMIO trace for the kernel, because the 3D stuff in this Matrox case only works with this proprietary kernel driver loaded. Anyway, I wanted to check, also maybe I should quickly go through the comments and see what else we have. But yeah, it's not nothing is shared here, and all the memory mapped I/O register writes are all different between ATI, NVIDIA, Matrox, number 9, SES, VR, and Cirrus Logic, and T-Zeng Labs, and all the other vendors that existed at one point at a time. So yeah, welcome everyone who tuned in. Thomas, I believe that's a black box VM, pretty old open box is arguably better, so people there don't care too much, but whatever. Comments, have I ever tried a tiling window manager? I only tried them a little bit. I have not yet ever gotten too used to them, but yeah, point taken. And anyway, so last but not least, so this was the first frame buffer write, so this was the first cursor. Most likely, if you, maybe actually I should decode that, but what I will probably do next is write a small example program to write this cursor stuff in there and see if the cursor changes, and then also solid fills, and try this freestanding booting our trusty transmitter thin client, network booting this into DOS with my bare metal stuff, and see if VESA BIOS extension, SVGA mode setting this, and then setting the cursor allows us to have hardware cursor, and from then do all the other advanced stuff. So what else was this here? This is whatever read write, whatever that was here. 1C, by the way, was this all 1C? By the way, let's, also this was 304. Read write. Actually, by the way, we have here write and write. So maybe, as it's maybe in the beginning, this stuff, it's incrementing 1 bit at a time here, sort of, whatever, and reading. So we can already put into our node, I'm pretty sure this should be something of read write here. This is most likely some DDC stuff to be decoded another day. Display data channel square C. Does this keyboard layout right now have okay, this looks ugly as fuck. J American asked, any way to automate the decoding of the hex value? So what you could automate, so the decoding of the hex values, of course, Novo NVIDIA reverse engineering folks have tools here in their NV tools somewhere here, probably of that or other NV tools fame. However, this is of course NVIDIA specific. So to decode this, like in this document, you would need to know which bits are which, what they do, like here in probably X cursor control. So like this kind of bits here for XGA or X window cursor and stuff. This is what some of these bits here would do. And you can only automate this when you already know what some of these bits are doing. What you could do, however, is write, and I'm pretty sure the NVIDIA people, the Novo people might have this somewhere, I guess, is small examples. Because as I said, next you would need to decipher all the hardware accelerated drawing, and for this you would need small examples. So basically have it as least as possible here on your X server. Like if you have other stuff going on, then it's even harder to find out what's going on. So it's best to have like next to nothing and only have an X window that is only with X core protocol or X render, or then OpenGL draw lines and fill rectangles and fill triangles one step at a time. And you could theoretically automate, and maybe the NVIDIA and ATI open source people have here already good tools. They have here certainly some of this stuff like NV tools, and there's also like there was like what did I see today? There was like Revenge, I think, Revenge, and certainly this reversing tools often have good names. I think one was Revenge of whatever that was doing. Revenge described a possible replace for superior auto detection of, this was some MMIO tracing of whatever. And some of the stuff has unfortunately already gone, like Radeon reverse engineering tool from before when ATI. Also, yeah, a lesson learned, dear vendors, if you don't give a specification, we just we only piss us off more, like NVIDIA's finger, NVIDIA's Linus Torvalds and my certainly joining finger. And yeah, you only make us hate you more, right? Instead of giving us nice specification, what does it cost you to give us such a nice document like Matrox and ATI Intel stuff, right? What does this cost you? With this, we don't ask for anything, just give us this bloody document where all the register values are noted down, and like backend scaler here, horizontal scaling and fun stuff. And you don't even, in my opinion, we don't even ask for driver, right? We write probably usually the better driver ourselves, and cost you nothing to give us a bloody documentation. It's not even too much of the most amazing trade secrets. Yeah, if you don't do this, you are sooner or later out of business, like Matrox, more or less. And yeah, instead of making friends, like giving a specification, you only make enemies of people wasting years of their lifetime decoding these registers. For automation, as I said, have small programs like drawing a small rectangle and triangle and stuff. And theoretically, you could automate this. Also nowadays, in terms of virtual machines, maybe another month I try to set up something with QEMU and hardware-assisted I/O MMU, I/O virtual machine or I/O memory management stuff. And theoretically, it should also be possible to fully have a Windows machine, right? You don't even need to. You don't necessarily have a Windows Linux driver. If you want to do this with a Windows driver, you would need similar tools like this amazing Valgrind MMTL memory mapped trace tool. And certainly, you do not necessarily want to write such Windows software. So nowadays, it's of course a pretty nice thing to just use maybe QEMU and hardware-assisted I/O MMU hardware path-through, and maybe instrument. If maybe it's done already, would surprise me if it's not yet done for NVIDIA reverse engineering. And but if it's not done, just like yeah, certainly it helps for everyone if the better virtualization and I/O memory mapped tracing tools we have, and do this with the original Windows driver, and just similarly, instead of Valgrind, but do this in QEMU and trace all the I/O MMU writes. And then similar, if you do this on Windows, I would suggest also to write a small direct 3D full screen application so that you have no I/O MMU, because if you have Windows, you have a clock blinking, all the Windows decoration, you would certainly don't want to have hundreds, if not gigabytes of trace logs there. So yeah, black full screen application, and then just one line triangle, textured triangle, and then vertex shaders. And certainly nowadays with all the programmable vertex shaders and fragment shaders, that is rather cumbersome, that you need to decipher all the instructions at architecture, similar to the Spark ARM previous video. Programmable GPUs, that is certainly extremely time consuming and cumbersome, and certainly theoretically this Matrox Parhelia has already some DirectX 8.1 or something programmable vertex and fragment shader. So later deciphering this instruction certainly rather time consuming and error prone, but as we have seen in terms of NVIDIA's Novo, certainly doable. Anyway, so this was I only wanted to check here one last look on this fun stuff to something. So this is the first. So this is mode setting. All this registers probably mode setting and general. Some of this also stride, which by the way we could theoretically check. We have here not Lure, also not BC. Thank you very much. Nothing on this machine. We have here 1920 multiplied, I think, by 4 bytes. So theoretically, some of this we should have a stride, the length of pixels in bytes in the VRAM. Theoretically, we might have this value here somewhere written. Of course, not that, but somewhere else. No. Maybe with 0. But maybe not. Usually this is part of the, no, but we don't have. But this kind of values should be programmed somewhere, wherever they are. But yeah, I think I wanted to say you could theoretically automate like determining with like machine learning, having your small example so that you run this on an NVIDIA ATI Matrox card as a small example. It's moving the cursor, and because this moving the cursor and changing the cursor shape and solid filling some rectangle and some triangles should normally leave some kind of handful of register writes, and so theoretically some kind of machine, like super simple machine learning of running this on Windows in a Windows machine, tracing this with IOMEM. You should theoretically kind of at least some, depending of course on the hardware complexity and how well you can pattern match this, but theoretically it should be possible that it could be automated, like fully automated, somewhat mostly automated Windows hardware driver tracing, and so that this automated program to be written, maybe if you are NVIDIA ATI Intel developer and open source tools are floating around for this, leave me in the comments below, that this pattern matching stuff spits out like cursor change this registers, like cursor change this registers, CRTC, whatever, where did we had, whatever, and so on. And mode setting, like mode setting, changing the video mode, this set of registers. Of course, it still would most likely involve some human interaction to decipher what exactly those bit locations are. But again, this is where I earlier said I wish there would be an international standard, like VGA standard for this hardware accelerated stuff, but unfortunately there isn't. And very theoretically, you could even write a driver like this, right? Fully automated, like boot Windows, log all the memory mapped IO registers, and just copy them all the trace, maybe in terms of deriving some loop parameters, so that you don't have like hundreds of megabytes of log. But very theoretically, you could write a first proof of concept driver, just replaying here this logs and like tracing mode settings, this resolution, then determining which parameters maybe somewhat automatically are the X and Y, like width and height resolution, and bit BLT X, Y, like run this Windows program, see where these values end up here in terms of bit BLT programming here, and so which are source, destination and stuff, and even somewhat automates this. Should probably, it's not the easiest thing to automate, but some stuff should theoretically be possible. So this was the first cursor. I only wanted to also, what more comments do we have there? Could you create a program similar to benchmarking where only draw one thing? Yeah, this is what I just explained. Diff, yeah, exactly that. By diffing also differences mean output difference. So yeah, I mean, diffing is what I've done here already, but what I explained is like machine pattern matching, of really spitting out these registers that are affecting that. And Paul, I looked at Google Fuchsia Zircon coming up for another day. One topic at a time here. So this was the first frame buffer read, then this stuff is reprogramming whatever, also 3.1c. We continue a couple of 5 minutes just to determine here maybe a couple of more. 3.1c we had here already, DDC was, yes, 304, whatever. So this is reading, whatever that is reading, 408. So this early stuff are some, you see this is 8100 something. These are some most likely some memory offsets here for whatever. So this is, the higher is the 10, 12, 30 are the cursor apertures. So this 8 here, this very long numbers, most likely some offset of whatever, and maybe some set buffer or whatever. We can lure, what is that in decimal? And yes, I use lure for a lot of stuff. So yeah, this is actually, wait a second, this is 128 megabyte, probably had. This card has 128 megabyte. So here, this is 128 megabyte. So this is, for whatever reason it is writing it in there, I have no idea. We can document this already. So this is our 128 megabyte for whatever reason. Maybe some whatever, maybe it's even, certainly this stuff also has DRAM controller registers, right? So this has some DDR2 memory controller stuff for whatever reason it needs to know that. I have no idea. Then 18 SS, wait a second, 18 we do not yet have. We have 10, whatever 18 is, has to be seen. Yeah, 1C, 10, so the 10 is, what did we have, 10 we had cursors, so this is changing the cursor apparently to some different cursor also. And then certainly some of them are certainly set buffer and so on, most likely. And yeah, I only wanted to say what it is because so it's changing some stuff. So obviously it's changing the cursor. You see this 30 and 10 are cursor offsets as far as I determined. So this is cursor here, 10, this we do not yet know. Maybe we better put it somewhere else then. Because these are, in my opinion, as far as I've seen, they belong together. And so it's setting the cursor for some reason and then reprogramming it just directly again. That would be 10, 20, 30, 34. So 34, 38 here. Whatever the, maybe some other bits here are bit depths. But anyway, then when it's moving the cursor, so this is moving the cursor, 30, 34, 30 here for the second or first or second video head. So it's changing the, because it's just, as I said already a couple of times now, it's just set a cursor to the beginning of the frame buffer address 0, and then it's changing it again because it wants then to use the frame buffer address 0 for the visible portion and filling it black for the Xorg server startup. This is why it's here the last thing before that, changing the cursor to another location and then filling it here. But yeah, anyway, that's it for the initial look here of this stuff. I hope you enjoy this and learn something and motivates you to do fun little hardware stuff as well. And that's it for this video. I will try this bit another day and see how far we're getting, and then certainly, as you see, and at the state of NVIDIA's open source Novo reverse engineering, however prone and time consuming this is also why I show you here how this is done, so people value more why developers like us are asking for documentation, what amazing time-consuming works the open source NVIDIA, Novo, and other, even some AT and Intel bits and pieces, and certainly other cards and other, console emulator, PS3, PS4, and similar stuff, also reverse engineering, and we still need to do for the PS3 anyway. But that's it for today. I have to go. I hope you learned something. One last look here at that. Comments in the audience, doesn't have this card limited vertex shaders. Yeah, it's not like direct 9 level, but it has direct X 8.1 or something. But it's like better than DirectX 8.1 or so shaders. So it has like, so they are not like shader model 2. Later in Parhelia's life, DirectX 9 application were becoming quite prevalent. Matrox acknowledged that the vertex shaders were not shader model 2 capable, but they were like includes 4 32 by 4 vertex shaders with dedicated displacement mapping engine, pixel shaders array with 4 texture units, and 5-stage pixel shader per pixel pipeline, 16 fragment anti-aliasing, and something of that sort. Yeah, so this is DirectX 8. It's like a little bit better than DirectX 8.1 and several DirectX 9 features compatible. So not too shabby, and I wish Matrox would have acknowledged the support they got from the open source G200, G400 drivers and would have released the specification. I said this already before. They, a decade ago, even asked for a p690 repository, but they never checked something in, which is really sad. Maybe they had some project, maybe at some stock exchange or something, some project that didn't went through because he was in p690 repository created. Here of Yannick Hennes sold of Matrox in 2008, but never something committed. Also, really said, hey, can you make us a repository? And then, here it is. And then it's like, here's a test file, and that's it. So I said this before, I mailed Matrox 3 times over a decade, like, hey, do you want to publish this something? Do you have some specification? I would love to do something because I have this card in for a decade already, but YOLO, whatever. That's life. And something that could have been a nice server second life there for Matrox, but as per usual with the open source friendliness with companies, it's usually only skin deep. And as I said in the previous gaming videos, if you want to see this card in action, previous video playing Quake 3 on this card, and as I said in this video, if they would have had an open source, like not this binary only blob driver, they could have potentially sold quite some quantity in open source compatible lens there in the beginning of the 2000s, back when this card was new some 15 years ago. But so is life, and this is what can grow companies or quickly kill them, because certainly on Windows they were not the most competitive, and as I postulated, some outstanding open source driver certainly could have been some sales boost. And I really wish companies would more often recognize this and not like play this stupid, it's our bloody intellectual property. What intellectual? But I also said, I speculated, because as if NVIDIA and ATI can't do hardware and they would need this register stuff to develop NVIDIA, GeForce and ATI Radeon stuff. The only thing is, maybe they feared at Matrox that they get sued if NVIDIA and ATI would see in black on white how this Matrox Parhelia works. Maybe Matrox feared being sued. Also, the amazing situation with software patents and the innovation they kill, that is the only valid only somewhat plausible reason, in my opinion, why companies like Matrox would not publish specifications in terms of patent lawsuits. Anyway, that's it for today. Steer asks in the comments in the audience, is this PCIe? So this is PCIe, but I actually got two, so they existed in all flavors. And in the meantime, I purchased here for this YouTube video, I like a decade ago, so this is a little bit darkish. So this is PCIe, as you may or may not see. I also have a PCI version. The PCI version is exactly the same. It just has a PLX PCIe to PCI bridge. Otherwise, the layout and everything is exactly the same, just on the back side. And the AGP version, I'm not sure. Maybe whatever. Maybe either the AGP version, I don't have it. But yeah, I got this. By the way, I said this before, a decade ago for $6.90. Not too bad of an investment for a spare testing card. Certainly at $6.90 is a price where it's fun to buy stuff from eBay. But yeah, PCIe native card, the PCI, at least the early Parhelia, by the way, the original Parhelia, probably native PCIe AGP, but this is a die shrunk p690, and yeah, the original Parhelia was actively cooled and maybe native AGP. This is native PCIe, and yeah, not too bad. Anyway, that's it for today, and I hope to see you soon for the next videos and live streams to come.